Modern business operations generate continuous streams of raw data. Spreadsheets, audio files, and pixel grids flow at velocities that outpace human analysis. Historically, traditional machine learning required data scientists to manually engineer and extract specific features from this information before a computer could process it. Deep learning removes that manual bottleneck through end-to-end learning. By utilizing networks with multiple layers, the system autonomously maps inputs directly to outputs without human intervention. This is achieved through hierarchical feature learning. The lowest layers of the network capture simple, local features, like straight edges and textures, while the higher layers combine them to identify complex, global concepts, like complete shapes or specific objects. This layered architectural approach is a mathematical model inspired directly by the interconnected structure of neurons in the human brain. But deep learning is not a universal solution that can be applied arbitrarily. To extract accurate insights, you must choose the precise neural network architecture that matches the inherent structure of your data. There were 3 foundational blueprints used to process information: feed-forward, convolutional, and recurrent neural networks. Auditing your data types and aligning them with the correct structural framework is the only way to move past theoretical hype and deploy models that drive measurable operational value. The most basic structural baseline is the feed-forward neural network, or FFN. This architecture is built explicitly for straightforward, highly structured data. This diagram shows a neural network where information flows strictly left to right. The yellow input layer receives raw data. It passes into the blue and green hidden layers, where neurons apply mathematical transformations. Finally, the red output layer delivers the final prediction. The mechanics mirror a factory assembly line. A raw order comes into the building, passes sequentially through discrete mixing and baking stations, and exits as a packaged cookie. The product never moves backward to a previous station. This rigid, linear processing is highly effective for tabular data. Businesses deploy FNNs to predict customer churn or flag fraudulent credit card transactions based on structured historical records. Because the data flow is strictly one way, FNNs execute simple decisions quickly. But if your data relies on complex spatial relationships or visual context, this rigid structure fails entirely. If you feed the pixels of a photograph into a standard FNN, the network processes the individual values, but loses all understanding of spatial context and where those pixels sit in relation to one another. To analyze spatial data, engineers rely on convolutional neural networks, or CNNs. The defining mechanism here is the convolutional layer. Learnable filters, or kernels, systematically move across the image grid to detect specific structural patterns. Following this scan, pooling layers reduce the data grid's overall size while retaining the most important visual features. Think of it like a quality inspector systematically examining a product, swapping out different magnifying glasses to hunt for specific types of microscopic defects. This spatial awareness allows autonomous vehicles to instantly detect and map bounding boxes around stop signs and other cars in real time. That exact same architectural logic applies to retail logistics, automatically identifying inventory as it sits inside a shopping cart. This image shows a chest X-ray, where a CNN has performed medical image segmentation, using its spatial awareness to map the precise boundaries of lung anomalies. Beyond healthcare and transit, CNNs are essential for automating product inspection on manufacturing lines and executing facial recognition for physical security. CNNs perfectly map spatial relationships in a frozen, singular image. However, because they possess no memory mechanism, they are blind to data that evolves over a sequence of time. Sequential data presents a unique challenge. The meaning of the current input depends entirely on the information that preceded it. To process timelines, we use recurrent neural networks, or RNNs. These architectures feature internal connections that allow data to persist as it moves forward. Each neuron contains a hidden state. This state acts as a memory bank, taking the output of the previous step and looping it back in as an additional input for the current step. Human conversations are sequential data. They only make sense because we actively remember the context of the sentences spoken moments ago. RNNs attempt to mimic this continuous context. But standard RNNs encounter a critical mathematical limit, known as the vanishing gradient problem. This occurs when the mathematical signals used to update the network become exponentially small over time, causing the system to rapidly lose its long-term memory. To solve this degradation, researchers evolved the architecture into long short-term memory networks, or LSTMs, and gated recurrent units. Gated recurrent units, or GRUs, are a streamlined variant of RNNs that use simplified gating to control information flow without a separate memory cell. LSTMs introduce specialized gating mechanisms into the node. These gates mathematically calculate what specific information is important enough to retain and what irrelevant data should be discarded. An LSTM operates like a highly skilled note-taker in a lengthy corporate meeting, filtering out the casual noise and documenting only the long-term patterns that matter to the final objective. This selective memory makes LSTMs the foundation for natural language processing. Businesses use them for nuanced sentiment analysis, complex customer service chatbots, and analyzing time series data for financial forecasting. By adding memory, LSTMs turn isolated data points into a continuous predictive context, allowing systems to understand evolving human interactions. Designing the theoretical architecture is only the first step. For a neural network to actually function, it must survive a mathematically intensive training phase. This diagram illustrates the backpropagation algorithm, the training process used to adjust the weight of connections between neurons. The top arrow represents forward propagation, producing an initial guess. The bottom arrow represents backward propagation, adjusting weights backward to improve the next attempt. During millions of these iterative cycles, the network risks a failure state called overfitting. Overfitting occurs when a network memorizes the exact, intricate patterns of the training data so perfectly that it loses the ability to generalize to new, unseen examples in the real world. To mitigate this, engineers use a technique called dropout. By randomly deactivating a fraction of the network's neurons during training, the system is forced to build robust, redundant pathways instead of relying on narrow memorization. Executing this constant forward and backward propagation demands massive computational complexity. Businesses must leverage specialized hardware, specifically graphics processing units and tensor processing units, to calculate millions of matrices simultaneously. Tensor processing units, or TPUs, are application-specific circuits designed to accelerate machine learning workloads more efficiently than general-purpose hardware. A brilliant architectural design requires both the physical computing power to execute the math and the structural guardrails to ensure the resulting model remains accurate in production. Deep learning provides a powerful method for extracting insights from raw information, but the practical utility of the network is contingent upon precise architectural alignment. Feed-forward neural networks process structured, tabular data, executing straightforward, linear decisions. Convolutional neural networks master spatial data, handling the visual scanning required for object recognition. Long short-term memory networks master time, utilizing sequential memory to analyze context and generate language. Selecting the wrong column ensures operational failure. An FNN cannot process a live security feed, and a CNN cannot maintain the context of a customer service interaction. Effective AI integration is not a matter of purchasing a generic product. It requires leaders to rigorously audit their data types and map them directly to these specific structural blueprints. Artificial intelligence is no longer an abstract concept. It is a highly structured, strategic toolset, built layer by layer to extract order from complexity.